Okay. Okay, so let's get started. I think I'm going to do things a bit upside down. I'm not going to ask for questions at the beginning right now because today's material is a little bit tricky, and I want to make sure that we get through it. It's both tricky and important. So we've been talking about sort of ways of creating new functions out of old functions, right? And we have a simple way of just adding or subtracting functions and multiplying them. And we have a slightly more complicated way of composing them, right? Taking the output of one and taking that as the input of the next, input of the next. The last way that we're going to introduce is the most complicated. It's the section 3.6. It's called inverse functions. So inverting functions. And so we start off with a question. Suppose we had a function. So here's our function. Here's the graph of the function. So suppose we have a function y, we have a function f of x, right? And this function is the sort that, suppose we have a function f whose graph, when flipped across the line y equals x, was still a graph of the function. Okay, so we have this function, we flip it across the line y equals x, right? And it turns out that still is a function. It still satisfies the vertical line test, right? Here it satisfies the vertical line test, and this graph is funny. When we flip it, it still satisfies the vertical line test. Okay. So this is the graph of another function, right? This is the graph of some other function, right? What's the relation? What's the relation between these two functions? What's the relation between these two functions? Okay, so to sort of give you a hint, let's think about this. If we have a point here, a comma b, right? Then can anyone give me the coordinates of a point on the flipped graph? B comma a, right? B comma a. This point, B comma a, is going to be on the flipped graph. Right? Is that clear? Right? If we take the x coordinate and change it into the y coordinate, and we take the y coordinate and change it into the x coordinate, right? Then we get a point on the flipped graph. Okay. And so now I'm going to ask you one of those questions which people look at me and it'll seem too simple or something. Okay. AB is on the graph of f. What does that tell you? What does that tell you? AB being on the graph of f, what does that mean? That's okay?
If you put in A, you'll get B.
Yes, that f of a must be. Okay, so now, same question. BA is on the graph of G. What does that tell you about BA? What does that tell you about G? Let's see, Shreya, how about you? You put in B, you get A, right? So G of B is A. Okay. Everyone okay so far? So Katie, just to catch you up, okay, we're doing something called inverse functions, and I'm starting off with the following setup. We have this function f, and it turns out that this function, when you flip it over the line y equals x, when you flip it with the line y equals x, you still get the graph of the function. Okay, so it's an unusual function. You flip it, it's still a function. Okay, and we're talking about what's the relation between those two functions. And we're noticing that we see a relation that if f takes a to b, then g takes b to a, takes b back to a. Okay. So what the relation is that they sort of reverse each other. They reverse each other's effects, right? They sort of they reverse each other's effects. Right? They sort of cancel each other out, right? Right? Another way of saying that is that right, that g of f of a, what's g of f of a? Right? G of f of a is going to be what? Not 0, but right?
Oh, okay.
It's going to be a, right? Right? Because f of a is b and g of b is a, right? And similarly, f of g of b, maybe I should write this using composition notation. Right? It's going to be b, right? So, in other words, g composed with f and f composed with g are functions that do nothing at all, right? They take in something and they hand you back the same thing. Okay, right? These guys are what's called identity functions. Are the identity. That is, they are the function that just hands you back what you give. Okay, and so these f and g, what's the relation? Right? They cancel each other. They cancel each other out. Yeah. Okay. Yeah. So we call such functions are called inverses of each other. G is the inverse of f is the inverse of g. Okay, so let me just put that down formally. Definition, f and g are called inverses of each other if f composed with g of x is x for all x in the domain of g, and g composed with f of x is x, again, for all x in the domain of f. Okay. So to give some simple examples, like if I have f of x is 2x, then what should be the inverse function? Be the function that cancels out what f does, right? So yes. So what function will cancel out the 2x? 2x again? If I want a function that sort of reverses the effects of 2x, right? F says, whatever you give me, I'm going to double it, right? The next guy wants to reverse that effect, right? So g of x will do what?
Give you the outcome.
It will. So you want a g that so that it takes the output and then gives you back x. Takes 2x and then returns back x. Well, Carolyn.
Would it be half?
Half, yeah, half x, right? Right? So, like g of x being half x is the one that cancels off this one guy multiplies by 2, this guy multiplies by half, right? And so it's sort of easy to see that if you take g of f of x, you're taking g of 2x, that's a half of 2x, well half of 2x is just x, right? And similarly, f of g of x is f of half x, well, double half x is just x. So these guys are inverses. Okay. And we usually write something like this, we abbreviate this, we notate this by saying that g is f to the negative 1. G is f inverse. This is how we read this. G is f inverse. Same thing, you could just as well write that f is g inverse. They're inverses of each other. And the standard thing to watch out for is that, remember that this is not the same thing as, it's not the same thing as 1 over f. Okay. So warning, f inverse is not the same thing as 1 over f. So maybe to make it a little bit, f inverse x is not the same thing as fx to the negative 1. Okay. I know the notation is confusing, but this is how people notate inverses. Okay, so just watch out. Don't confuse these two things. When we write f inverse, we mean the inverse. When we write fx to the negative 1, we mean 1 over x. And 1 over f inverse. This guy here, this thing is, right? This thing is this. Fx to the negative 1 is 1, is the reciprocal of fx. Okay. 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 Let me do a slightly more difficult example. A slightly more complicated example. F of x is 2x plus 3, right? So f is the function that takes what you give it, it doubles it, and then adds on 3. Right? Doubles it and then adds on 3. Okay. So what should the inverse function do? Well, I mean, it composes it, yeah. It should take in the output and give you back x. That's true. But just think about it in terms of a procedure, right? Like f is this person, and whatever you give him, he doubles it and then adds 3 to it. Okay. Now there's another person who's gonna reverse that, right? So what should that person do? Take 3 off and then halve it, right?
So you always just put a 1 over whatever the 2x is?
Are you asking if it's the reciprocal again? It's not the reciprocal. You don't know what you're asking.
No, well, it's just. Well, it was okay. So let's say it was
Yeah.
Let's say it was fx equals 3x. Would it then be f is 1 over 3x?
No.
G?
No.
Okay.
No. If fx is 3x, just think of it as a procedure, right? F is the guy that takes whatever you give him and then triples it,
Okay.
right? So what's G going to do?
Take what you have and
And then
divide it by 3.
divide by 3, right? So G would be a guy who takes in something and then divides it by 3, right?
Okay.
But it's not the guy that, it's not 1 over 3x.
So how did you know it was 1 over 2 instead of x over 2?
1 over 2x.
Oh, because you got the, because you had g of x, say it was.
It's 1 over 2x.
Okay.
That's the same as x over 2. So g of x here, f of x being the guy who doubles and then adds on 3. Well, g of x should be the guy that subtracts off 3 and then divides the whole thing by 2. Right? So it should reverse the things, reverse the steps. Yeah, one.
Why do you divide the whole thing by 2, whereas, like, in the first thing, only x is multiplied by 2?
Yeah, you have to think about the process, right? If suppose I give you $100, right? I give $100 to F. F doubles that and adds on 3, right? how do you get back to the $100? We have to subtract out the 3 and then divide the thing minus 3 over by 2.
So you basically take everything in the function and just do the opposite of it.
That's right, in the reverse order. Okay.
So is it the reverse of the order of operations too then, or we're going backwards in the reverse?
In a few seconds, I'll show you guys sort of a procedure by which you can calculate it inverse. So let's hold on and we'll get to it. Okay. So, but just to check that this works, you could check g of say f of x. Right? G of f of x is going to be f of x. Well, that's 2x plus 3 minus 3 everything over 2. Right? And you see what happens. You get 2x plus 3 minus 2. That's 2x over 2. That becomes x. And the other way also. G of x. Right? If you take 2 of g of x and add 3 to it, well, you get x. You get x here. Okay. So, in terms of rules, these are the guys whose rules cancel each other out. Graphically, it's one guy's graph is the flip of the other graph, right? Suppose I have this graph, though. This graph, and I flip it across the x-axis, right? I'm sorry, flip it across the line y equals x. Then I get this, right? So my new graph, is that a graph of a function? Well, no, right? It's not the graph of a function. So this guy doesn't have an inverse, right? And so we ask, to make this a bit more precise, say, what functions have inverses? What functions all have inverses? Not all functions have inverses, right? And so we can sort of get a hint from what we just did. We say, well, the graph of f, if f is invertible, then the flipped graph has to be the graph of the function. Right? The flipped graph has to be a graph of the function, right? When you flip it, it has to pass the vertical line test. Right? When you flip it, it has to pass the vertical line test. In other words, flipped graph must pass the vertical line test. Okay, and so this leads to something that people call the horizontal line test. Right? So when you flip it, the flipped graph has to pass the vertical line test. What does that tell you about the original graph? What does it tell you about the original graph? Julian? When you flip it, it has to pass the vertical line test, right? What does that tell you about the original graph? When you flip it, it can't be the case that it intersects a vertical line in 2 places. Well, what does that say about the original function? That it can't have the property that.
Doesn't that mean it is inverse if it hits 2?
No. What I'm saying again?
I don't want to.
So, okay, let me see if I. So you said. Okay.
So if it hits 2 points, it means that you can invert it if you want to?
No. Remember, if you flip it and it hits 2 points, that means that the flipped guy isn't the graph of the function, right? So the flipped guy, this guy isn't invertible. Isn't invertible. Okay, so this is a bad thing. So if we look, so do we really need to flip it? Well, we can just look at the first guy and say, if the flipped guy hits a vertical line in two places, that tells you that the original guy must have hit a horizontal line in two places, right? Okay. So this is what's called the horizontal line test, right? If a horizontal line hits the graph of f in two places, then f is not invertible. Then f is not invertible. Okay, but this is really nothing. This is really sort of like a nothing test. Well, I don't even think we need to give this thing a name. Right? It's just that you want the flipped guy to pass the vertical line test, right? Which is the same thing as saying that the original guy passes a horizontal. Sorry, I said it backwards. You want the flipped guy to pass the vertical line test. In other words, the original graph must pass the horizontal line test. So the example which we basically already hinted at is f of x equals x squared, right? Does this guy have an inverse function? Is there something that will reverse this? Right? If I say like f of x equals 9, right? Then what is x?
Square root 30.
You don't know, right? You don't know. It could be either 3 or it could be negative 3, right? There's no, right? You don't know which one to take as the, to define, right? So at inverse of 9 could be what, right? It could be 3 or it could be negative 3. There's trouble, right? So it's, this guy doesn't have an inverse. Right, and you can see that in the vertical line test, the horizontal line test. By saying, well, look, you know, these 2 points, 3 and negative 3, get mapped to the same height. Right, so there's no way to invert it. So like, so for example, if we're looking at test grades, say, in the class, right, and I had a function mapping each person to a test grade, right? If they're all different test grades, then I can have an inverse function, right? I can go, you know, from the person to the grade, and I can go from the grade back to the person, right? I could have an inverse function in that case. But if 2 people got the same scores, then I'd be in trouble, right? If I got the grade, I'd be like, I don't know whose grade this is. It could be either, you know, Alex, or it could be Carol.
But does it matter though if it's the same, if you know that they have the same grade?
Okay,
Okay, I'm thinking it's too large a system.
That's the point is can I create an inverse function or not? Right? Can I create an inverse function or not? So if everybody got different grades, I can. If everybody got the same grade, then I wouldn't be able to do that. It's true that, you know, from a you know, if I were handing down papers, then it wouldn't really matter. I just have to give everybody, you know, the same papers. But that's not work. That's not what I mean. Okay. Is this sort of making sense what an inverse function is? Right. An inverse function, you've got one function that it goes one way, and then you want to go backwards, right? And you want to create a function that does the reverse of that, right? Okay. And this leads to something that this leads to the definition. and this is sort of a tricky one, so this often confuses people, so let's pay attention right now. If whenever x1 is not equal to x2, we have f of x1 not equal to f of x2, we call f a one-to-one function. A one-to-one function, we usually get just 1-1, or it's also called injective. One-to-one function. So just like we were talking about just now, if everybody got different grades, the function associating going from the person to the grade would be a one-to-one function. But if two people in class got the same grade, then it would not be a one-to-one function. Right? Because then two people would be mapped onto the same grade, onto the same score. And it may be clear at this point that the function is invertible if it is one-to-one. Right? If it's a one-to-one function, then there's an inverse to it. Right? Just like what we just said, if everybody got mapped to a different grade, then we can go backwards. We can go from the grades back to the kids. Right? And if and only if. It's one-to-one. So if it's invertible, it's one-to-one. If it's one-to-one, it's invertible. I think this might be the first time that we've introduced this term if and only if. So let me just emphasize it a little bit. Right? If and only if means, so a function is invertible if it is one-to-one. Right? That means one-to-one implies invertibility. Right? This first statement means one-to-one implies invertible. A function is invertible only if it's one-to-one. So that's the opposite statement. Invertible implies one-to-one. Okay. So these are, when we say if and only if, we mean that the implication goes in both ways. If you go on in math, you'll see this if and only if so much that in math classes we have an abbreviation. We get tired of writing if and only if, and we usually write if. Just like we also write one and only one. Okay. Okay. So. Any questions? Any questions? Anyone confused? I feel like there's a slight cloud of confusion in the room. Is it true? Or are my senses off?
So you might do it only certain examples.
Okay. So, okay. So, okay, so here, so let's talk about finding numbers. How do you find numbers? So, like suppose you have a function and it is one-to-one. How do you find? How does one find an inverse? Okay. And here's the strategy. Let's say that f of x is y. Okay. And we want to find out what f inverse is. want f inverse. Okay. And so f of x is y. Well, it should be, right? If f inverse exists, then f inverse of y should be x. Right? Right. If f of x is y, then f inverse of y should be x. Right? That's what the inverse function should do. It should reverse it. Right? So here's the strategy. Solve fx equals y for x. Right? Play with this guy until you get x on the left side, and then you get something else on the right side. Right? That function of that thing on the right side ought to be f inverse y. This should be f inverse y. Okay, so let's just start off with the simple example that we did before. F of x is 2x, right? So we say right, this 2x is y. Okay. Right. And then we solve for x. We solve for x, we get that x is 1/2 y. Right? X is 1/2 y, and so this ought to be f inverse of y. Right? F inverse should be the function that takes y to half y, the function that divides things by 2. And indeed, that's what we saw earlier. F inverse, right? If f is the doubling function, then f inverse should be the halving function. All right.
So is that the same thing as saying is 2x equals y? Is that the same thing as saying f of 2x equals y?
F of x equals y, right? So we start out from here, right? We say, take your function, set it equal to y, and then solve for x. Maybe I should write that down. Take your function, set it equal to y, solve for x. Okay. Then that thing is going to be f inverse of y. Right. The second example we did, f of x is 2x plus 3. Okay. So we take 2x plus y, 2x plus 3 equals y, right? And we solve for x again. Okay. How do we get back to x? Right? That's the question. How do we get back to x? Well, to get back to x, we need to subtract off 3. And then we need to divide by 2. Right? How do we get back to x? Okay. Well, you have to take off that 3 first, and then divide by 2. You want to undo whatever f did. You don't like what f did to you. Right? You had something really nice, f came and messed it up, and you're wondering how to undo it. Right? Well, this is how you figure it out. Well, I want to get back to x. Well, I need to subtract off the 3, and then I need to divide by 2. Yeah, if only light were vertical. Okay. Okay, so let me ask you guys to do a simple one. I think it should be a simple one. F of x is 1/3 x plus 2. It should, if you're following along, it should take not take more than a minute. should not take more than half. Who would like to say? Swami.
So it will be x equals to 3y minus 6.
X equals 3y minus 6. Is that right?
I got that.
Okay. Right, so I mean, just let's work it out. Sorry. 1/3 of x plus 2 equals y. Equals y. And we get y minus 2 equals 1/3. So x is going to be 3 times that, right? 3y minus 6. Right, so the inverse function, f inverse 1 is 3y minus 6. Yeah, Lauren.
Okay. When I was in high school, we like switched the x
X and Y.
y. Is that the same?
It's the same thing, it's the same thing. But I think it actually makes more sense to keep it this way.
Okay.
Okay, so here's I was just about to talk about that. Here you have this function, right? And the way you want to think about it is like, it goes from the x world to the y world,
Okay.
right?
Oh, so if you just switch the x, y, you're not going to like.
The inverse function, properly speaking, should go from the y world back to the x world,
Okay.
right? So it actually makes more sense to keep it this way.
Okay.
I know that
But either way, you find the same answer.
either way you find the same answer, and it's sort of, if I write f inverse x is x minus 3 over 2, that's true. That's true. It's the function that takes in something and then subtracts 3 from it and divides the whole thing by
Okay.
2.
But you would rather us do the other way.
Yeah, because it actually shows that you understand the notion of domain and range.
Okay.
Right? You're going, this is the domain of f, it goes into the range of f. The inverse function should go from the range of f back to the domain of f.
Oh.
Right? Any other questions? Alex, did you get it?
Yeah.
Good. Okay. So what happens if we throw in something like this? F of x is say x squared plus 1. Right? And we try to calculate the inverse. You know this is not going to work, right? This is not going to work. So what happens when we do it? Right? How do we find out? Right? Well, we get f of x is y, so then we get x squared equals y minus 1, right? And then we get x is then plus or minus the square root of y minus 1, right? And so there's trouble, right? Because we don't know what should f inverse equals which one? Is it plus or is it minus? Okay. But let me make one comment. So if I look, so here's the function f of x equals x squared plus 1. Right? It's not invertible, but if I look at it only on this half, right? If I say x has to be positive, now it is invertible, right? This function is invertible. Is invertible, right? And the inverse function is going to be root minus it's going to be the positive line, root y minus 1. Right, so sometimes, and you'll do this in the future, the function might not be invertible everywhere, but you throw out parts of the domain. You restrict your domain, and you say, okay, well, it may not be invertible everywhere, but it's invertible here. Like the sine function, right? The sine function is very, very not invertible, right? It's not just 2 to 1, it's infinite to 1, right? There are infinitely many points that get mapped to the same value, right? But if you restrict the sine function to say negative pi over 2, pi over 2, then it is invertible. Do you have a question?
I was just asking if my graph was for the question, because I was getting confused.
If the graph was what?
Was like related to the question, because I was getting really confused, but now I see that. They're obviously is.
Okay.
So I didn't want to ask you.
Okay. I'm sorry, I made you ask. Okay. Okay, so another example. Sorry. Going back to finding the inverse function. Let's go back. Let me give you a more complicated example. This is number 22 in the text. X minus y cubed minus 1. So again, the question is find the inverse function. Katie, how about I make you do it?
Is it,
Tell me how you do it. So you take this thing, you set it equal to y,
so you do y plus 1, and then would you take root 3?
cube root.
And then you add 3.
And that means the inverse function. Good. That was the one. It's not going to, the questions we'll ask about finding the inverse function will not get much harder than this. So I hope you guys now have some sense of this. What we'll do in the future, in the next chapter, is basically starting from very simple functions, linear functions, then going to quadratic functions, and then going to more complicated functions. You do trigonometric functions, exponential functions, these sorts of more complicated functions, and then you throw in inverses, right? You say the inverse of the exponential function, which turns out to be the so-called logarithm function, right? You'll see you have trigonometric functions and you invert them. You have inverse trigonometric functions, right? And these are all functions that are important. Yeah.
So if you were given the equation of an inverse function and asked to find the domain and range, how would you do that? Or do we need to know how
Don't
to
ask me this.
Okay.
Well, we sort of did this game earlier, and it's sort of the same game, but what you can do is so here's the function, right? What's the domain of this function? All the numbers, right? And what's the range of this function? Again, all the numbers. So you know that this line actually goes from here to here. Well, the inverse function is going to do the opposite.
Wait,
It's going to go from the range back to the domain.
okay.
So it's actually not too bad.